Hello and welcome to today's session on circular motion. And what we're going to do is apply circular motion equations to a particular case of motion over the top of a hill. The circular motion equations are from Newton's second law. We know Newton's second law, F equals ma. For motion in a circle, we can talk about the centripetal force that acts towards the center. So it's mass times the acceleration, and there's two forms of writing the acceleration: v squared over r, or F equals m omega squared r, where r is the radius of curvature, omega here is the angular velocity, and v is the speed around the circle. So it's just, again, applying Newton's second law to a new case. This is the question we're looking at today then. So we've got a diagram and it shows vertical forces acting on a car of mass 800 kilograms, and it's traveling over the top of a curved bridge. The downward force acting on the car is its weight, and the upward force acting on the car is the contact force provided by the road. The radius of curvature of the bridge is 20 meters, and the speed of the car is 12 meters per second. So there's four parts, and we'll go through the four parts. Part A, calculate the centripetal acceleration of the car. Part B, use your answer to part A to determine the contact force R when the car is at the top of the bridge. Part C, show that the car will lose contact with the top of the bridge if its speed exceeds root gr, where g is the acceleration of freefall and r is the radius of curvature of the bridge. Part D, use your answer to part C to determine the minimum speed of the car for which the car loses contact with the top of the bridge. Okay, starting off with part A, we want to find the centripetal acceleration of the car. And if we look at the question, what are we given in the question? In the question, we're given the radius of curvature, we're given the speed of the car. So we can use a relationship. So let's start with part A over here. The acceleration is equal to v squared over r. V is 12 meters per second, and the radius is 20. So we need to square 12 meters per second and divide that by 20. So the answer we get to two significant figures is 7.2 meters per second squared. So that's part A done. Part B, we need to use the answer to part A to determine the contact force when the car is at the top of the bridge. So if we look at the diagram, we've got the weight acting downwards, and going in the opposite direction is the reaction or the contact force or the support force, it's sometimes written as. So we need to think about the resultant force between the weight and that contact force is equal to the centripetal force. So what we're saying is that the weight acting downwards, W, minus R, is equal to the force, centripetal force, mv squared over r. We know that we can write the weight, put that here, weight is equal to mass times g, where g is the acceleration due to gravity. So we want to find the contact force. So we make r the subject. R is the subject, so r is equal to the weight minus mv squared over r. Now it's just a case of substituting our numbers into the equation and working out a value. So as we said, r is equal to w minus mv squared over r. W is mg. So let's just put all our terms in. The weight is 800. G is 9.81. Times v squared, which is 12 squared. But if you recall, we've calculated the acceleration in part A, so we can put that straight in there. But I'm just writing that all out there for you. So all we need to do now then is put that into the calculator. Again, we want an answer to two significant figures. So to two significant figures, I get a force of 2,100 newtons. So that's part B done. We now need to think about part C. So we need to show that if the speed exceeds gr, so it will lose contact with that bit. So let's go through part C. Okay, so if the car loses contact with the surface of the bridge, what that means is that the contact force goes to 0. So let's just write that down. So part C. So we know when it's on the bridge, when the car's on the bridge, we have this situation, mv squared over r. So w minus r is equal to mv squared over r. That's when the car is on the bridge. So when it loses contact with the bridge, that means the contact force goes to 0. So that means you're left with this situation where w is equal to mv squared over r because it's not in contact with the bridge. From part B, we know w is mg, so mg is equal to mv squared over r. We need to make v the subject because we're trying to show what the speed is. So we want to make v the subject. You can see that the m's will cancel out. So we can cancel out the m's. And if we make v the subject, we bring the r over there. So v squared will be equal to gr. And v is equal to the square root of gr. So that's part C done. Right, we'll go on to part D. So I'll get a new page so we can do this on the board. So part D, we need to find the minimum speed of the car for which the car loses contact with the top of the bridge. So part D is straightforward. We've done all the hard work in the previous sections of the question. So part D, all we need to do now is use that relationship. So we've said V is equal to root GR. So all we need to do is substitute into that equation. And again, we need a value to two significant figures, and that will be it. So put that into your calculator to two significant figures. You get 14 meters per second. Okay, so we've tackled this problem in that particular case of motion over the top of the hill, and we've applied the circular motion equations. Remember, it comes from what we've looked at previously, which is Newton's second law, so F equals ma. It's a resultant force that's providing that centripetal force acting towards the center of curvature. And as we've seen before, we can calculate the acceleration as v squared over r, or omega squared r. And it's dependent on what we're presented with in the question, which form that we will use. So we'll leave that there today. Thanks for watching, and I will see you on the next video.